Hello all. Today we are going to discuss the topic transmission electron microscopy and its application in metal organic frameworks. How we can use it for metal organic frameworks imaging. So starting with this, why do we need electron microscopy? As we know that we have optical microscope, which is used very frequently, has a resolution only up to 10 raised per minus 6, means at micron level. But by using that resolution, we are not able to image the molecules, image the atoms. So so for atomic or molecular level resolution, we need something different. Hence, we use the concept of electron microscopy. It can provide a resolution up to 0.2 nanometer, right? And why it happens? This happens due to the fact that as electrons have very short wavelength in comparison to the visible light. That is why we are getting higher resolution by using electrons. Further, before going into the principle, let's understand what actually happens when an electron strikes the specimen. Here we are having incoming electrons. When incoming electrons do strike on specimen, then several things can happen. The electrons can backscatter, or there may be emission of secondary electrons, or there can be emission of positive electrons, or there can be emission of X-rays as well. Or if the specimen is sufficiently thin, then it can transmit the sample. It can transmit without scattering, or if it scatters, there are two ways of scattering. The first way is the inelastic scattering, and the second way is the elastic scattering. So if inelastic scattering happens, we are equipped with the microscopy technique, which is TEM, or head of TEM technique, which we will be discussing in our coming lectures. And also the if secondary electrons dominate, then we get the beautiful phenomena of surface electron microscopy. If Auger electrons get emit, then Auger electron microscopy comes in picture. So there are different microscopy techniques which arises from the electron when electron strikes on a specimen. So we will be discussing TEM over here. Further, this is the outline of the microscope, how actually microscope looks like. Starting with the electron gun at the in the very starting, then we have a pair of condenser lenses for the illumination purpose. Then we have sample holder, then a pair of objective lenses with immediate lens as well, and with its apertures. And then finally we have projector lenses and fluorescent screen to do the image recording. And this system is useful for magnification purpose. We will be discussing this in the coming slides. So this is how the transmission electron microscope looks like. This is the beautiful picture taken. This is the whole machine, the big machine, and it costs more than $4 million. Why this is so costly? This is so costly because of its complex instrumentation, and the resolution is a bit tedious to do. That is the solving resolution, or to do resolve the things. It is a bit tedious one. So that is why TEM microscope is so much costly, right? Because of the complex technique, complex instrumentation things. So let's get into the principle. This is the electron source, condenser lenses, then objective lenses. So let's discuss their uses. So starting with the electron source, this electron source actually emits the electron. This is a very beautiful example shown over here. Field emission gun. How it emits the electron? Actually, it emits the electron uh, after the generation of electric field. When initially electric field is generated, and due to this electric field, atoms uh, atomic electrons start getting attracted towards the electric field, and in this way the electrons are generated, right? So from the electron source, electrons are generated. Then we have a pair of condenser lenses. What condenser lenses do is they actually control the brightness and the convergence of beam, right? Convergence of beam, what is the requirement of this? Actually, we allow a specimen to handle or to bear only a specific amount of electron beam, right? The specimen can bear only a specific amount of electron beam, and that is why controlling the convergence or amount of the electron uh, that is going to get over the sample should be controlled by a lens which is known as condenser lenses, right? Uh, condenser lenses, right? So actually in TEM, in electron microscopy, how is the lens made? Actually, this is not the conventional optical lens. It is actually electromagnetic lens. Whether it is condenser lens, whether it is objective lens, or whether it is a immediate lens or projector lens, they all are electromagnetic lens, right? Electromagnetic lens actually works on the principle that uh, this consists of a solenoid. This solenoid generates the electric field, and this solenoid is connected to an electric field, is connected to a current, and this current produces magnetic field. And this magnetic field helps to deflect the electron or to direct the electron for convergence or divergence properties, right? So this is how the lens system is made. So after the beam converges, it is projected on the sample. This is a thin specimen what we are having, and after the thin specimen, we have twin objective lens with a couple of objective lenses. This actually forms a diffraction image over here that we are seeing over here, that this is the diffracted electron at the objective back focal plane. And also, instead of convergence over here, we can also project it further by using projector lens on the fluorescent screen, right, to have an image of the same of the complex, right? So in this way, we have seen that a TEM machine can be used in two different modes. The first is the diffraction mode, and the second is the imaging mode. So this is the actual principle of the TEM microscopy. So after this, we will be seeing one thing, this objective lens, what it actually does. This objective lens actually controls the contrast of the image, right? In any image, right? Oh, right, we can see over here how the figures are presented over here, how the surface boundaries are separated from each other. This is actually decided by the contrast. Contrast is actually can be defined as the how one object or one entity is separated from other. This is known as the contrast, right? This is called as the contrast, how one is separated from the other, it from its neighboring part. So how this contrast is generated, we will be discussing this. Actually in TEM, we are having two different contrast modes. The first is the amplitude diffraction contrast, and the second one is the phase contrast. In amplitude or diffraction contrast, here the concept of diffraction is used. The concept of diffraction means, as we know, uh, at particular Bragg angle, as we know from the single crystal XRD, there we know at a particular Bragg angle the diffraction pattern happens, the wave construct, right? So the same concept is used over here. At a particular Bragg angle, the waves having same amplitude and which are in same phase, they construct. And for various different theta angle, for various different theta Bragg angle, we are having different contrast, a different pair of electron, different pair of electron beam is there, right? So the deflection in the so the uh, difference in the deflection of electron as per the Bragg angle is concerned gives the contrast, right? So this is actually so amplitude or diffraction contrast is actually related with the Bragg angle. At a particular angle theta, we are having a particular contrast. So different angle theta gives different contrast, right? So in this we are having two imaging modes, which is the first one is bright field imaging and the second one is dark field imaging. In bright field imaging, actually the direct rays are allowed to pass. If direct rays are allowed to pass, we are having the whole image bright, and the diffracted ray is blocked. If diffracted ray is blocked, then that portion will appear black. So mean in a specimen, the reason which is diffracting the specimen, if there is any defect which is diffracting, then it will appear black, right? So this is the principle. But in dark field, the thing happens reverse. This is the incident beam, and this incident beam is actually blocked, and if incident beam is blocked, the image will appear black. And if only diffracted wave is passed, if diffracted wave is passed, that portion appears brighter, right? So in this way, uh, the the contrast is generated. The second is the phase contrast. How the phase contrast is generated? The phase contrast is generated by using the fact that difference in phase difference of the electron waves. This is used to generate the contrast. And how this phase difference is created. This phase difference is created by using, first this is created by the specimen, and then further with the objective lenses to have the contrast, right? We can see over here, this is the mechanism which is used to explain crystalline samples mainly, and this gives higher resolution, and that is why phase contrast is also known as higher resolution TEM. Means whenever, so next time whenever you hear the word that phase contrast, means it is the HRTEM, high resolution transmission electron microscope. And the main thing in this all is the sample preparation. Actually, for electrons to pass through the samples will be electronically very transparent, or the thickness will be around 100 nanometer, right? So this is the main tedious process in this. So starting in this, we are having a silicon wafer on which resin is embedded, on which particle is put it, and this is sandwiched with the two silicon wafers, and it is further put it in the copper wire. And after that, the copper wire is cutted with a thickness of 0.3 millimeter, and further mechanical grinding is done to make it further thin, which is the thickness around is 0.1 millimeter. Further dimple grinding is done, and then further iron milling is done to make it further thin of around the required thickness. So this all process seems to be very one by one, but this is actually a very tedious and a very sophisticated process, which is the sample preparation process. So this has to be done very quick, very carefully. So after knowing all this principle, sample preparation, how the contrast is generated, we will be discussing how metal organic frameworks are imaged by using this technique. As you know that metal organic frameworks are very beam sensitive materials. They are easily amorphosized, and the typical HRTM technique. What is typical HRTM technique? Actually, typical HRTM technique is the normal HRTM technique. The normal conditions is a set of conditions at which HRTM technique used for general samples, not for the metal organic frameworks, right? So that is why MOF suffers the challenge. And why MOFs are so prone to structural damage? Actually, these are the reasons. The first is the knock-on damage, right? Knock-on damage occurs at the very high acceleration voltage. And the second is the heating effect, which is pronounced as the high voltage. This happens because the surface becomes highly charged. Due to this, surface starts heating, right? And the third is the radiolysis effect. Radiolysis effect means this is the ionization damage, which is pronounced more at the low voltages. What is this? This is actually when electron bombards on the when electrons comes on the specimen. Sometimes it ejects an electron from the K shell, right? And after this, an other electron from the next oxygen starts emitting. Then something else start happening instead of this, right? So this is the main cause. This is the main structural cause in case of MOF imaging, right? This is the main cause for the structural damage in metal organic framework. So how the developments in the technique has took place for improving all this. So initially the TEM was used with the low voltages, but it has several disadvantages, like it gave the poor resolution. Why it gives the poor resolution? Because as you know that resolution depends on the acceleration voltage as well. We need a sufficient high voltage to have a better resolution, right? So that is why the resolution was poor. And also at low voltages, radiolysis effect was still there, and and the beam penetration was still weak. So then technique improved. Then there came a cryo-TEM. Cryo-TEM means HRTEM was performed at very low temperature, that is liquid nitrogen temperature, which is minus 196 degrees Celsius. So this improved the beam stability. But again, since low voltage was used, radiolysis effect was still there, which was doing the structural damage to the metal organic frameworks. So then came the year 2017, in which Professor Yuan from KOS, Saudi Arabia, with his lab group, he perf he performed the metal organic framework imaging by using the DDC camera coupled with cryo-TEM. So he used this combination DDEC camera, which is known as the direct detection electron coupled camera, with cryo-TEM, and he was successful uh, in imaging the metal organic frameworks by using low electron volts at the very high acceleration voltage, and this also gives a better resolution, which was around 2.1 angstrom, right? So after this, the efficiency of the TEM improved. And what was the reason behind this DDC camera? Actually, there was high detective quantum efficiency of the DDC camera was there, right? Further, we are having various imaging techniques like head-off system, high angular diffraction technique. The first one is this, and the second one is the integrated differential phase contrast system technique. They all have a good resolution, good contrast, good tolerance to the noise, and uh, due to the since head-off time images at the high angle, and also in this technique, they are able to a good contrast and differences in the imaging of the high-end lighter elements, like in metal organic framework, as you know that there are metal nodes, right? Metal nodes have metals, cerium, zirconium, right, and have oxygen. So these two elements are having a high difference in their atomic mass, right? So they are able to differentiate the two, right? Further, how we are going to utilize in metal organic framework, how we are going to utilize this technique in MOF, right? We will be discussing it. As we know that for knowing the periodic bulk structure, we are having diffraction based techniques like single crystal XRD, or for a signature we take the PXRD, right? But for imaging non-periodic local structures like the grain boundaries, like the defects, actual crystal structure, or sometimes the inclusion of the guest molecules, we will be using the microscopic techniques like TEM. So in the coming slides, we will be discussing one by one. So this is the example in which we will be discussing the how imaging of bulk structure of MOF is done, right? Imaging of bulk structure. So this is the isoreticle of MOF 74, which are having hexagonally arranged channels. Here we can see that by increasing the ligand size, the pore size can be increased, and this is the actual HRTM image we can see over here. And from this HRTM image, the pore size was calculated, and pore size was actually matching with the data taken from the d-spacing of single crystal XRD. So in this way, the pore size of channel was actually imaged from the HRTM image, and this was done by Professor Hexiang Deng during his postdoc in the laboratory of Professor Omar Yagi at that time. And also, this is also the actual HRTM image of the PCM 333. Right? There was having a mesopore size of 3.7 nanometer, which also helped in the determination of the space group, which was FD3M. So, heterogenetic framework is also successful in imaging the actual bulk structure of the MOFs. Further, we can also image surface structure of the MOS. Right? As we know that in UI 66 there is some defect. Sorry, in UI 66 there is surface dependent termination of the modes. Surface dependent termination means the crystals are terminated by using a particular entity, right? Like we can see over here, like the BDC linker terminates the 111 surface, like this is the actual HRTM image that we are seeing over here, actual HRTM processed image, and this is the structural model. Hmm. So we can see that this surface of this crystal grain is terminated by by using this ligand, and this is the projected image of the rainbow color. This is given for having a better visual contrast, right? And with this also there happens that 100 surface and 111 truncated surface is terminated by the middle clusters, and this was also imaged using HRTM. We can see over here, right? This is the actual process HRTM image, this is the structure model, and this is the rainbow color image for having a better contrast, right? So you can see these are the spots, right? And from here the grain is separated, right? We can see this is the linker. After this, the surface is terminated, and there is also a second beautiful example in which MIL101 was synthesized using three different techniques. The first was using by no modulator, the second by acetic acid as modulator, and third was HF as the modulator. We can see over here all of the surface are having a different degree of completeness, and this was actually imaged by HRTM. Right, this is the image. So this is the actual processed HRTM image. This is the projected image, and this is the actual this is the structural image for better understanding. So the actual surface was imaged, the actual surface, the nature of the surface was known by using the MOFs. Further, we can also know the interfacial structure of MOF, right? How this is the actual process which I am mistaken, and this is actually zoomed over here. We can see that after a particular boundary, there is a reflection of the crystal. A reflection of crystal means that we can see over here means after this boundary, they are the further extension, the further two side extension is refracted, right? The reflection of each other means there is twinning of the crystal. This is example of Z-fade MOF in which twin boundary separation is there. It was actually imaged from the HRTM. This is also known as arm to notch configuration, and at the interface the pore size is large, and this was imaged using HRTM. And this also explains the beautifulness of the MOF, right? Although MOF is having the complex structure, having ligands, having metal nodes, the complex structure, this also shows the properties like conventional crystals, right? Although having this complex structure. Further, the defects was also imaged by using MOF. Like here we are having this perfect UIU66 crystal, right? And this is the actual HRTM image of the missing linker defect, in which we can see that the contrast is missing along a particular direction. We can see there is a contrast for the ligand, but the ligand contrast is missing over here along a particular direction, along a particular direction. So this was actually imaged by using MOFs, right? So in this way, the defects in the MOF was imaged by using the contrast we can see over here. Like further, we can also image the guest molecules. Like this is the image of the MIL crystals, in which inside the MIL crystal inorganic peroxide was made, and after this it was imaged. This is the actual HRTM image, and this is zoomed image. The resolution is 10 nanometer, and we can see there is an unusual brightness. This brightness confirms that the inorganic peroxide was formed inside the MIL crystal, right? So this in this way the guest molecule was imaged, and and there comes the other example of the fate crystal, in which CO2 was there, means the gas was trapped inside the fate crystal. So this is the actual process research image, and was further zoomed, and the actual molecular dimension of CO2 was measured for the confirmation. And this all the scene was taken at the cryo temperature, means at the liquid nitrogen temperature. Why this was taken at the cryo temperature? Because cryo temperature is a good technique to image the gaseous molecules, because at cryo temperature the desorption of gas can be prevented, and hence gas can be properly imaged. Further, using by knowing all these applications of TEM in the MOF, we have seen that this can come up with various applications. Its use can come up with the various applications in various areas, right? And finally, a sincere thanks to the paper in communications chemistry, from where I have taken all this content, right? And final thanks to you all for listening to me. Thank you.